today we will start the topic of classification of partial differential equations. There will be a few lectures on this topic, and we concentrate essentially on second order linear partial differential equations for the classification, and you will see why this restriction as we go on. So, first of all, we will start with the basic question: why classification? So, in many branches of mathematics, we do classify objects of study. For example, in linear algebra we classify square matrices into class of symmetric matrices, orthogonal matrices and positive definite matrices. Why do we do that? So, in order to, this we may group a particular set of PDE whose solutions have common qualitative or quantitative properties, so that we will recognize, given a PDE, into which group it falls. For most of the 19th century and early 20th century, efforts were more concentrated in finding formulas for various initial and or boundary value problems of equations of mathematical physics. And that is the reason in that period people essentially concentrated on three types of equation. The first one is wave equation. So, describing vibrations in small transversal vibrations of a string, the longitudinal vibrations of a rod, electrical oscillations in a wire, etc. And this equation is a prototype of hyperbolic equations. So, we will define what is an hyperbolic equation as we go on. So, this typically the hyperbolic equations they have qualitative properties connected with the solutions of the wave equation. So, this is in one dimension, and it also has in 3 dimension it models vibrations of a membrane, propagation of sound waves, light waves and electromagnetic waves in a medium. And then comes the equation of heat conduction, and this is a prototype of parabolic equations. So, this is another classification in those. So, one of the again physical phenomena of heat conduction. So, they were interested in that. So, this was studied in great detail. So, it also describes diffusion of a chemical substance in a medium. As such, it is also called diffusion equation. So, heat equation or diffusion equation. And the last one, a steady state process, physical process, that is a physical process that does not change with time, is generally modeled by a Laplace or Poisson equation, and this is classified as elliptic equation. We have one more mathematical region for doing the classification. Given a differential equation, whether ordinary differential equation or a partial differential equation, a basic problem associated with an ODE or PDE is the Cauchy problem or an initial value problem. So, for a second order ODE, u double prime bu prime plus u equal to g in an interval on the real line. So, we prescribe two initial conditions u x 0 equal to u 0, u equal to is missing there, equal to u 0, and u prime x 0 equal to u 1. Okay. So, initial position and initial velocity, if you interpret in Newtonian mechanics. So, this describes the dynamics of a particle. So, if you give initial position and initial velocity, we should be able to tell the dynamics of that particle. And in case of ODE, there is no restriction on u 0 and u 1, they are arbitrary. Okay. So, such a scenario changes when we come to a PDE. Okay. For example, here consider a linear second order equation in some domain in Rn. So, you can just take R2 for example, and what is the Cauchy problem associated with this equation? Cauchy problem you can give it on a hypersurface. Okay. For example, in R2 this is nothing but a smooth curve. Okay. So, in higher dimensions it is an n minus 1 dimensional surface, and that is called a hypersurface. And so, suppose it is represented by an equation of the form f x equal to 0 with grad f x not 0 for all x on that surface gamma. And this condition just indicates that there is a well defined normal to the surface gamma at every point, and it is smooth. That is why you assume this gamma to be of class C k. And on this surface we prescribe the initial data or Cauchy data is called for the equation 1.1, and so this is the prescribe the Cauchy data on gamma. So, you give its initial position and then you give the normal derivative. So, this del u by del u denotes the normal derivative of u on gamma, okay, and these two are prescribed. So, similar to the ODE problem. So, two initial conditions for the ODE are given. So, similarly here it is a second order PDE. So, we are giving two conditions, and unlike ODE, what we observe is that in general this u 0 and u 1 x are not arbitrary. So, this requires a great deal of computation, which I am avoiding here. So, that is the difference. What makes this difference is the fact that, so this we did not face in the case of ODE, but in case of PD we do face this, and so the main reason for that is whether gamma is a characteristic surface or not, characteristic surface with respect to the given PDE. Okay. So, here is a definition: a point x bar on the gamma is called a characteristic point for the equation 1.1. So, important. So, you are connecting now the initial surface gamma and the PDE, that is important. If this grad f x t superscript t denotes transpose of a matrix, and A is coming from the PDE, that matrix A. So, it is coming from the coefficients A I j, so which I denote by this. So, it is a variable matrix. So, if A I j are constant, then it is a constant matrix, otherwise it is a variable constant. So, there should be x bar here, okay, sorry for that. So, at that point, so if this happens, it is called a characteristic point, and if each point of the surface gamma is a characteristic point, then gamma is called a characteristic surface. So, if gamma is a characteristic surface, then the Cauchy problem is called a characteristic Cauchy problem, and if gamma is non-characteristic surface, then the Cauchy problem is called non-characteristic surface, non-characteristic Cauchy problem, and generally non-characteristic Cauchy problems, they have solution that can be shown, and in case of already first order PDE, we have seen this characteristic in some other form, namely transversality and other conditions. Okay. So, it is similar to that. So, in general, so this that is the difference. So, and this definition of the characteristics obviously depends on the PDE coefficients, and that is why we want to classify the PDE into different groups. So, this is the mathematical reasoning for studying this classification of PDE. Having said about that, about the classification, there are many equations of importance that lie outside these classes. What are these classes? Namely hyperbolic, parabolic and elliptic. So, I just list a few of them. There are plenty of equations. So, one is this Schrodinger equation from quantum mechanics, it is written here. So, it looks closer to the heat equation, but qualitatively its solutions are more like wave equation. And also you observe that this I is square root of -1. So, we have to deal with complex functions as solutions. So, in case of heat equation, wave equation and Laplace equation, they were all real valued functions, but in case of Schrodinger equation, we have to deal with complex functions as solutions. So, the next one is, again this is very much studied in the literature, commonly called KdV equation, this Korteweg-de Vries equation. It is also a nonlinear equation of third order. Okay. So, u x x x. Okay. So, here by looking at the nature of the solution, it is classified as dispersive equation as opposed to diffusion equation. Okay. So, the linear equation of KdV, which existed much earlier, is called Airy equation. So, just you remove the nonlinear part in the KdV equation, you get this Airy equation, and then there are equations from fluid dynamics, Navier-Stokes equations. So, that is a system of equations. So, that also does not easily fit into this classification, and there are many more. Okay. So, you can just see the literature. So, in what I am trying to say here is this classification is incomplete. So, that's it's not that all PDEs will fit into one of these three groups. There are many important PDEs which lie outside this three groups, and in the modern theory of this subject, especially after the 1950s. So, there quite a bit understanding of partial differential equations, and now we see the classification as hypoelliptic and non-hypoelliptic. So, even to make a definition of that, we have to develop many tools, so which is not possible in this first course on PD. So, we will do some basic thing in this course. So, begin with a simple situation just to understand what is this classification and how we are going to do this classification. Okay. So, take the simplest example. So, a second order linear PDE. So, for the as far as the classification is concerned, only the second order derivatives matter. So, that is why I written only on second order they highlighted, and then LOT means it is lower order terms. Okay. Just concentrate on the highest order terms. Okay. To qualify it as a second order equation, so at least one coefficient Aij should be not 0, that is what I have written it. Otherwise, if all Aij are 0, then we are getting first order equation. So, the lower order terms, whether linear or non-linear, it does not matter as far as the classification is concerned. Okay. So, here, so I denote by A, capital A, the matrix of the coefficients, and that is a real symmetric matrix. Okay. That A is real symmetric matrix, and so this part Aij del square u by del xi del xj is called principal part of the equation, and that is written in the matrix notation as del x transpose A del x u. Del x denotes the gradient vector, and x signifies we are differentiating with respect to x variable. So, we are considering the equation in some open set in R n. So, that we denote the points in that open set x, because then we are going to change the variable x to some other thing. So, then we write it as del of that variable. Okay. So, that x signifies the differentiation is with respect to x. Okay. So, this I have written it here. So, it is the gradient vector, and superscript denotes the transpose of a matrix or a vector. From linear algebra, we learn that since A is a symmetric matrix, there is an orthogonal matrix, it is also called a rotation matrix, R such that R transpose A are equal to D. So, R since R is an orthogonal matrix, R transpose is also equal to R inverse. Okay. So, that is the knowledge we take from the linear algebra, and D. So, in essence what it says is a symmetric matrix is diagonalizable. and we can arrange the diagonal elements of this matrix D in the following way. So, lambda 1, lambda 2, lambda p minus lambda p plus 1 minus lambda plus p plus q and rest are 0. So, here we are collecting the positive eigenvalues of A, negative eigenvalues of A and 0 eigenvalue. Of course, A can have all the positive eigenvalues, all the negative eigenvalues. So, it cannot have all the 0 eigenvalue in this case, because A is not a 0 matrix. Okay. So, that is what we are writing now. So, lambda 1, lambda 2, lambda p are the positive eigenvalues of A, minus lambda p 1 etcetera are negative eigenvalues. So, there are p positive eigenvalues, then q negative eigenvalues and r 0 eigenvalues. So, total number should be n. So, p plus q plus r equal to n, and since A is non-zero, so it has at least one non-zero eigenvalue. So, that means either p is bigger than or equal to 1 or q is bigger than or equal to 1. Thus, the quadratic form associated with A, okay. So, this is also quadratic form associated with the given PDE. So, again let me just go back. So, in this summation Aij del square u divided by del xi del xj, you replace that del square u by del xi del xj by xi xj, and that is how you get the quadratic form associated with the matrix A, and matrix A comes from the PDE. So, this is also quadratic form associated with the PDE itself, and then you change the variable, you change from xi to xi tilde equal to r transpose xi. So, r is coming, r is the matrix that diagonalizes A, r is the rotation matrix. So, that using the diagonal process. So, you just get that quadratic form takes the diagonal form. So, there are no xi I tilde xi j tilde. So, it is purely a diagonal form, lambda I xi I tilde square corresponding to positive eigenvalues, and then we have a term corresponding to negative eigenvalues. So, of course, the rest are 0. So, you just they will not appear. Okay. And in a sense, what we are going to do for the classification, again going back to the PDE, we want to somehow get rid of the mixed derivatives del square u by del xi del xj I different from j. By finding suitable change of variables, we want to make it just a diagonal term. So, pure second order derivatives del square u by del xi square, similar to this diagonalization of the quadratic form associated with the matrix A. And we can do one more transformation, put eta I equal to square root of lambda I xi I tilde for I equal to 1 to p plus q. So, wherever you see that. So, I want to absorb this lambda I into xi I tilde, that is what I am doing, and that gives me this only plus ones and minus ones, nothing more, and this is called the canonical form associated with A or the quadratic form associated with A. So, we get only some diagonal terms and coefficients are also either plus 1 or minus 1. One difficulty, immediate difficulty we see is this obtaining canonical form. We have used the diagonalization of A and arrived at this canonical form, but that is not the only way one can arrive at a canonical form. So, there are many different ways. So, here let me just give you one example in R 2. So, you consider this quadratic form q x 1 x 2 equal to x 1 square plus x 1 x 2 plus x 2 square in R 2. So, I can write this quadratic form. So, there is x 1 x 2. So, I want to remove that. So, in 3 different ways, in fact, you can write in many more ways, but I have just written here 3 different ways how you can write q. Okay. So, something square, something square, something square, something square. So, I can use all these 3 different change of variables in order to write q in its canonical form. So, canonical form is not unique, but what is unique is, and that is again from the linear algebra, the number of positive eigenvalues p, the number of negative eigenvalues q, they are invariant, and this is called Sylvester's law of inertia. So, whatever change of variables you use to reduce a given quadratic form to its canonical form, the number of p and q will not change, and that is an important observation, and based on this invariants p and q, we are going to classify the PD. Okay. So, now we immediately connect this observation from linear algebra to our PD. Okay. So, now just again use that rotation matrix and you change the variables x to x tilde, then so this gradient vector of u with respect to x variable changes to gradient of u with respect to x tilde variable by that rotation matrix, and that you put in the equation back, and you see immediately that we obtain the principal part in diagonal form. Still there are lambda i's. So, we will also remove them by one more change of variable. And now you change x tilde to y. So, again just you want to absorb this lambda I in x I tilde, and that is very easy. So, you put y I equal to x I tilde by root lambda I, and that converts the principal part into a diagonal part del square u by del y square, and with coefficients only plus and minus 1. So, you just look at equation 1.2, you see that the coefficients are only, there are p plus 1s and q minus 1s, and this is referred to as canonical form of the principal part. So, we are not bothered at this stage about the lower order terms, the first order terms. Okay. So, we are just concentrated on the second order terms. So before defining the classification terms, so in case of variable coefficients, so when a I j are also functions of x, we wish to reduce the principal part into canonical form of the form 1.2 if possible. Okay. So, that is a big question whether we can do it or not. So, just that will come little later. So, let us now. So, here only 3 cases are considered, namely p equal to n, in that case q equal to r equal to 0, and p equal to n minus 1, q equal to 1 and r equal to 0, p equal to n minus 1, q equal to 0 and r equal to 1. So, in the first case all the eigenvalues of A are positive, and in the second case n minus 1 eigenvalues are positive and 1 negative eigenvalue, and in the last one there are n minus 1 positive eigenvalues and 1 0 eigenvalue. Okay. So, depending on this cases, we call the equation by a suitable name. Okay. Again the name nomenclature comes from geometry. So, just let me just tell you that. So, in R 3 the level sets of the quadratic lambda 1 x 1 square, lambda 2 x 1 square, sorry for that. So, it is lambda 1 x 1 square plus lambda 2 x 2 square plus lambda 3 x 3 square. So, if all the lambdas are positive, the level sets of that quadratic are ellipsoids, and if 2 of them are positive and 1 is negative, it is hyperbolic. So, the same terminology we use for the classification of PDE. So, PDE 1 is called elliptic equation if p equal to 1, or by changing the sign we can also assume q equal to n. So, either of them p equal to n or q, all are positive eigenvalues or all are negative eigenvalues. So, hyperbolic if p is equal to n minus 1 and q equal to 1, or again by changing the sign you can assume p equal to 1 and q equal to 1. So, in these two classification there are no 0 eigenvalues. So, in the first case when p equal to n or q equal to 1, the quadratic form is called definite, and in the other case it is called indefinite. So, in the definite case either it will have all the time positive sign or negative sign, and in the second case, that hyperbolic case, it will have it takes both positive and negative. So, we will come back to the other case in the next class. Okay. Thank you.